Welcome to Daily Papers, the podcast where we break down the latest and most interesting academic papers into something you can actually understand.
Today, we're talking about something we all use but maybe don't think about too much: maps. Specifically, can the smartest new AI models actually read one?
I mean, my phone's GPS gets me around, so I assume AI is pretty good with maps, right?
That's what you'd think. Your phone uses a very clean, simple kind of map, but what about the complex, messy maps that city planners, geologists, or emergency responders use? The ones with complicated legends, multiple layers of information, and strange symbols.
Ah, the ones that look like a modern art project gone wrong, full of dotted lines, cross-hatching, and a dozen shades of beige.
Exactly. A new paper asks if today's top AI models, specifically large vision language models or LVLMs, can make sense of those. These are the AIs that can look at a picture and describe it or read text. Think of models like Gemini or GPT-4.
The paper is called FRIEDA, Benchmarking Multi-Step Cartographic Reasoning in Vision Language Models. That's a mouthful, but the core idea is pretty simple. They've built the ultimate map reading exam for AI.
The researchers realized that existing tests for AI were too easy. They either used maps that were more like simple charts or focused on only one skill, like navigation. No one was testing if AI could perform complex, multi-step thinking on the kinds of maps professionals use in the real world.
So they created this new benchmark called FRIEDA, and to do it, they didn't create clean new maps. They pulled them directly from public documents, geological surveys, environmental assessments, urban planning reports. These are the real deal.
And the questions they ask are tough. They're designed to test what the paper calls cartographic reasoning. It's not just about finding a location, it's about understanding the relationships between things on the map.
They break it down into three main types of spatial reasoning. The first is called topological.
That sounds complicated.
It's actually pretty intuitive. It's about how things are positioned relative to each other. For example, a question might be, does this state park share a border with the proposed new highway? Or how many schools are located within this flood zone? It's about concepts like border, within, or intersect.
Okay, that makes sense. What's the second type?
The second is metric reasoning. This is all about measurement. A question might be, using the map's scale, what is the approximate distance in miles from the power station to the coastline? The AI has to find the scale bar on the map and do the math.
And the third must be about direction.
You got it. That's directional reasoning, using the compass rose or north arrow on the map to figure out things like, what is the orientation of the river in relation to the main town? Is it to the northeast, the southwest?
But what really makes FRIEDA difficult is that the questions often require multiple steps and sometimes even multiple maps.
Right. The paper gives a great example. The AI is shown two different maps of the same area and asked a question like, what is the name of the historic resource that shares a border with the priority funding area?
Wow, so the AI would have to first look at the legend on one map to figure out what a color or pattern represents a priority funding area. Then it has to look at the other map's legend to figure out what a historic resource looks like.
And then it has to find those two areas, see where they touch, and finally read the name of that specific historic resource off the map. That is a serious mental workout.
So this is the big test. They took 11 of the most advanced AI models out there and put them through the FRIEDA exam, the moment of truth. How did they do?
Well, to put it bluntly, they failed. Pretty badly.
Really? Even the big famous models?
Especially them. The very best models, which are considered state-of-the-art, scored below 40% accuracy, less than half the questions right.
That's a failing grade in any school. How does that compare to people?
That's the most shocking part. The researchers also had human experts take the same test. The humans scored an average of nearly 85%.
That is a massive gap. It's not even close. So where are these super smart AIs going wrong?
The paper did an error analysis, and the number one mistake was misinterpreting the legend. The AI would see a blue hatched area but think it meant commercial zone, when the legend clearly said it meant residential zone. It's a simple mistake, but it causes the whole reasoning process to fall apart.
So it's like they're trying to read a book without knowing the alphabet.
Exactly. The second biggest problem was that multi-map reasoning we talked about. When the AI had to align information from two different maps, it often got confused and couldn't integrate the data correctly.
So why does this all matter? Is it just about an AI getting lost on its way to the coffee shop?
It's much bigger than that. Think about critical tasks that rely on this kind of map reading. Disaster response teams need to overlay flood maps with infrastructure maps to know which roads are safe. Scientists need to compare geological maps to plan for earthquakes.
If an AI can't be trusted to read the map legend correctly, you definitely don't want it making those high-stakes decisions.
Precisely. This paper is a huge reality check for the AI world. It shows that while these models are amazing in many ways, they lack a fundamental understanding of the visual language of maps.
So, FRIEDA isn't just a test, it's a roadmap. It highlights a huge, persistent gap in AI abilities and gives researchers a clear benchmark to work towards.
The goal isn't just to build AIs that can describe a picture, but to build ones that can reason about complex symbolic information, just like a human expert would. And this paper shows there's still a long way to go.
That's all the time we have for today. Thanks for tuning in to Daily Papers.